Hey folks, welcome for part two. We've been talking about equilibrium, and now we're going to talk about Le Chatelier's principle. Okay, so here's the definition and a little analogy. Let's look at the picture first and see if we can figure out what this means. So imagine two buckets of water connected at the bottom. That's like equilibrium, right? There will be a balance across the top, because the water can flow back and forth as needed between the two. It's not a perfect analogy because this is not really very much of a dynamic equilibrium. It's more of a stable equilibrium, but it works for this analogy. So we have an equilibrium with two buckets of water connected at the bottom. Now, if we add water to one side, what happens? Well, water will flow from that side over to the other side until they are balanced again, now at a higher level, but still balanced. So, right, you have a system at equilibrium, you introduce a disturbance. In this case, we're adding more water to one side, and the system responds by shifting towards a new equilibrium. Okay, now let's look at what it says here. It states that when a change is made to the conditions of a dynamic equilibrium, the system moves to counteract the change, causing changes in quantities of reactants and products. That is, a reaction at equilibrium will respond to a disturbance in such a way as to counteract the disturbance and reach a new equilibrium. So there's that same definition again, and the concept kind of here of balance. And equilibrium is a nice system at balance. However, it almost never holds, right? Something always happens. There's some disturbance in a natural system, just like in your life, right? You're in balance and then something happens. You have to find a new balance again. And so that's Le Chatelier's principle. Chemically, there are two common types of disturbances that we will go through in detail here. So one is adding or removing one of the reactants or products. And the second is adding or removing heat, that is, heating or cooling the reaction. And the example throughout the series of slides coming up will be hydrogen plus iodine and hydrogen iodide. Okay, so let's first look at adding or removing a reactant or product. And we'll just focus on the left-hand side for now. Let's say we first changing reactants. If we add more hydrogen to a system at equilibrium, what happens? Well, this is a perfect analogy to the water picture below, right? We're adding something more to the left side. The effect will be to lose what you added and produce more onto the right side. And so that's exactly what happens, right? And we call this a shift to the right, meaning the system is at equilibrium and then you add H2 and the rate at which product is formed increases. So you create a little bit more product until a new equilibrium is reached. Equal rates again, but now different concentrations. Okay, so let's look at B now. If you remove some hydrogen, so now we've basically produced a deficiency. It's like taking our water analogy here and taking a scoop out from there. That's supposed to be a scooper. Right? So now the system will flow back to replace the hole, right? So you're basically producing a hole and shifting to the left to make up for that. Now, I've used this term a shift to the. What does that mean? Well, first the reaction must initially be at equilibrium, then disturbed from equilibrium, and now two things can happen. A shift to the right means that more reactant will be consumed and made into product until a new equilibrium is reached. So a shift to the right means shift to the product side, means make more product. A shift to the left means that the product will be consumed and made into reactant until a new equilibrium is reached. So shift to the left means shift to the reactant side, means make more reactant. Okay. Now, let's look at the bottom. This is the new part. We already did the top. So we did changing the reactants, and now how about changing the products? If we add more hydrogen iodide, we essentially now have an excess on the product side, right? The equilibrium is disbalanced with too much product. So we will see a shift to the left that will reach a new balance. And if we remove product, we can shift to the right to make more product, as long as there's enough reactant there. So this is actually a good example of maybe an industrial process, right? If you have a process producing, say, ammonia from nitrogen and hydrogen, it reaches equilibrium, it basically stops making more ammonia, which is what you want. So if you can go into the reaction and continually remove ammonia or remove product from the reaction, then you will cause a continual shift to the right and continue to make more product. So you can remove the product that you want, and then it will make more. You can remove the product that you want, and it will continue to shift to the right. And so that's one way to manipulate equilibrium to get more product or higher yields. Okay, so that's adding or removing reactant or product. And the key takeaway, if you add something, it shifts away from that. If you remove something, you've produced a hole or a deficiency, and it moves in to fill that. So add, move away, from, remove, move toward. Now, changing the temperature is like adding or removing heat. And if we have an exothermic and endothermic reaction, we know how it reacts to heat. Recall these pictures, right? Where an endothermic reaction has to absorb heat in order to make products. It has a delta H that is greater than 0. We can include heat as essentially a reactant in this reaction, right? Because without the heat, the reaction doesn't go. So heat is like a reactant that's required for this to go. And then for exothermic reactions, of course, heat is released. And so heat is a product of the reaction. It's not a chemical product, but it is a product of the reaction. And so once we include heat energy into a balanced chemical equation, the concept is really just like adding or removing reactants or products as before, but now we're talking about heat, right? So if we add heat, or let's say we increase the temperature, we can look at equilibrium and figure out what happens. So let's look at the top, an exothermic reaction. So an exothermic reaction, heat is a product, right? Delta H is less than 0. Well, if heat is a product, and we're going to, let's say, add heat or increase the temperature of an exothermic reaction, it actually slows the reaction down in terms of producing product. It's going to cause a shift to the left, right? So if you have a reaction that gives off heat as a product, it's at equilibrium. If you increase the temperature, it will make more reactant. It'll go backwards. However, if you cool it, if you remove heat, you'll cause a shift to the right because you've now essentially removed a product, right? You now have a deficiency. You have a hole. The system will shift to replace that, and so it'll shift to the right to increase heat. Endothermic reactions are just the opposite. If we add or increase the temperature, it's like adding a reactant that causes a shift to the right. Just like the water bucket analogy. However, with an endothermic reaction, if we remove heat or if we cool the system, then that's essentially like removing a reactant. We will see a shift to the left as product turns back into reactants. Okay, so I know that there's a lot between these two slides here and here, but just remember again, if you add something, equilibrium will shift away from it. If you remove something, equilibrium will shift towards it. Okay, so here's a question for you. According to Le Chatelier's principle, what will happen if nitrogen is added to this reaction at equilibrium? Right, okay, so nitrogen is a reactant. We're going to add something, it shifts away from it. So the reaction will shift to the right. What will happen if hydrogen is removed from this reaction? Right, so it doesn't matter if, before we kind of picked a reactant, but here there are two. It doesn't matter if we remove nitrogen or remove hydrogen, or if there is a third reactant. Any one of them would satisfy this requirement, right? So in this case, it could be nitrogen, it could be hydrogen, it doesn't matter in terms of the concept. So what will happen if hydrogen is removed? We're going to take this away, which means we need to replace it, right? And so we'll see a shift towards the thing that was removed. It will shift to the left. Now, flip the question on its head and say which change will cause this reaction to shift to the left. And the three options are adding something or none of the above is the fourth option. So a shift to the left would be produced by adding more product, right? Because now we'd have an excess, we need to get rid of it, we need to shift to make more reactants. Okay, here's a whole bunch of questions. Here's the reaction of nitrogen and oxygen to form nitrogen monoxide. It is a reversible endothermic reaction as shown in the chemical equation below. Predict whether the equilibrium shifts to the left, toward reactant, or to the right, toward product, in response to the disturbances listed below. All right, so there's one thing here, right, that we need to pay attention to in the text. It's a reversible endothermic reaction. So what does that mean for heat? That means that heat is a reactant. All right, like that. Okay, so I will let you pause it and go ahead and go through this for yourself. Okay, and now you're back, and here are the answers. The great reveal. So if you add heat, it shifts to the right. If you cool it, it shifts to the left. If nitrogen is added, shift to the right. Nitrogen monoxide is added, shift to the left. Some oxygen is removed, shift to the left. Some nitrogen monoxide is removed, shifts to the right. Okay, there's a good infographic from Compound Chem, which I took the left column from in the slides. So here's the whole thing. It's Compound Chem's a pretty good website for these chemistry infographics. But this one is all about equilibrium and the Chatelius principle. Notice there's a third thing that we could talk about, which is pressure, which we didn't talk about that. But we did talk about changing the concentration and changing the temperature. And so you can check out this slide to see that in another way. Or better yet, go to compoundchem.com and or search equilibrium there and you'll find it. All right, so this wraps up section 6.3. There's only 2 parts. We are now done, and make sure you're getting into the textbook to read this section, working on homework, and yeah, let me know if you have any questions. Take care.